Hello, in this video we'll be working through Unit 7 homework problems 13 through 20, and these deal with slope fields. Number 13, we're trying to draw the slope field for the differential equation dy dx equals x plus y. So we can really start at any one of these ordered pairs, but I like to start by looking at my differential equation and see if there's some kind of pattern I notice. Or I might start by just asking myself, when is the derivative going to equal 0? So if all we're doing is adding the x and the y coordinate, the slope is going to be 0 when x and y have opposite values. Or at 0, 0, for example. So at 0, 0, the slope is 0. At 1, negative 1, the slope is 0. 2, negative 2. Negative 1, 1. Negative 2, 2. And then we can, sometimes I'll ask, when is the slope going to be 1? So it's going to be 1 at 1, 0. And the reason I like to start with 1, well, I start with 0, but then go to 1 next is because a slope of 1 is easy to draw. It's easy to visualize a 45-degree angle. So I've got that point there, and then the slope is also going to be 1 at 2, negative 1. So 2, negative 1 here. And then it looks like maybe on the diagonals, the slopes are the same. So far, that's what I'm noticing. So I'm just going to finish off my diagonal. So at 0, 1, yes, the slope is 1. At negative 1, 2, negative 1, 2, yes, the slope is 1. And so we've got that pattern there. These all should have a slope of 1. I didn't draw them all parallel, but they should be. Okay, so let's try the next diagonal. If I look at the point 2, 0, 2, 0, the slope there is going to be 2. So I'm just imagining going up 2 and over 1, and how steep would that line be? And that's how I'm drawing my slope of 2. At 1, 1, the slope is also 2. At 0, 2, so along this diagonal, the slope is 2. And again, these should be parallel to each other. I'm doing the best I can. And then our next diagonal, we've got 2, 1, so the slope there is 3. So I'm visualizing going up 3 over 1. How steep would that be? And it probably doesn't, when I'm drawing it, it probably doesn't look that different from my slope of 2. So it's hard to freehand these. And then we've got 2, 2, the slope is 4, so I have to get even steeper without being vertical. And then at this last point, 2, 3, the slope is going to be 5, so even steeper yet. And then let's go along our remaining diagonals. Start over here. This is negative 2, 1, and the scale isn't labeled here, but I guess I'm assuming that I'm counting by ones in both directions. So at, what do we say right here? At negative 2, 1, the slope is going to be negative 1. So negative 45-degree angle. And then at negative 2, 0, the slope is negative 2. So I'm picturing kind of going down 2 over 1, and how steep would that line be? So there, and I'm going to draw them parallel on that diagonal. The next diagonal, for example, negative 2, negative 1, the slope's going to be negative 3. So imagine going down 3 over 1, and how steep is that going to be? It helps if you have a ruler that you can kind of hold on your paper. And then negative 4 for the next diagonal, and then negative 5 for that last one right there. Okay, let's look at our next one. Here our differential equation is dy dx equals x minus y. So for x minus y, at 0, 0, the slope is 0. And then at 1, 1, the slope is going to be 0. And 2, 2. And negative 1, negative 1. Negative 2, and so on. The slope is going to be 1 at 1, 0. And then I can just kind of guess or figure out where it's going to be 1 whenever the x value is 1 more than the y value. So 2, 1, for example, slope's going to be 1 there. So along this diagonal, we can check each individual 1, but the x coordinate is 1 greater than the y coordinate, so the slope overall is going to equal 1. Let's look at the next diagonal. So at 2, 0, the slope is 2. So again, imagine going up 2 over 1, and how steep would that be? So about like that. And I can check here on the diagonal, this is 1, -1. So at 1, -1, the slope is also 2, 2, 2. Oh, that was really bad. Those should all have all been parallel. Let's try that again. 2, 2, 2, 2. Oh my goodness, this is difficult. 2. Okay, well, imagine those are all parallel to one another. And then my next diagonal, so like 2, -1, 2 minus -1 is 3, so that has a slope of 3, so I'm going to even get a little steeper. Those all have a slope of 3, and then 4, and then 5. Okay, now up here, this is the point 2, 3, again, assuming that our scale is 1 in both directions. This is 2, 3, so 2 minus 3, the slope is going to be -1 here. -1, -1, -1, -1, -1. And at 1, 3, 1 minus 3 is -2, the slope is going to be -2. So picture going down 2 over 1, how steep would that be? About like that. So these are -2, and then that pattern continues. These are -3. Oh, that was bad. -3, -4, -5. Our next one, differential equation, is dy dx equals -y over x. -y over x. So we're going to get, well, when x and y have the same value, well, when they're both 0, we don't get anything. 0 over 0 is indeterminate, so we're going to leave that blank. When x and y are both 1, the slope is -1. When they're both 2, the slope is -1. When they're both -1, the slope is -1. So when x and y are the same, the slope is -1. When they're opposite, the slope is +1. So 1, -1, -1, 1, -2, 2, 2, -2. And then let's check this point next. So 1, 0. 1, 0 is going to have a slope of 0. When the x coordinate is 0, no, when the y coordinate is 0 and the x is not, we get a slope of 0. So except at 0, 0. Like so. And then let's see what else. What about our y-axis? So our y-axis, x is 0. And that slope would be undefined. We'd get if we have a non-zero number over 0, that's approaching infinity. So we've got vertical slopes here. So that's kind of strange. This is looking pretty odd. And then we've got, let's see, 1, 2. 1, 2 has a slope of -2. This seems very symmetric. It looks like I can just reflect quadrant 1 across the y-axis. Let me test that theory over here. At -1, 2, I have a slope of +2. So yeah, that did work out like that. And then let's jump back over here at 2, 1. 2, 1, the slope is -1/2. So down 1 over 2. -1/2. About like that. And that looks almost exactly like my -1. Let's try that again. Okay, and then over here at 2, 3. 2, 3, we have -1.5 or -3 over 2. So down 3, right 2. I'm not even sure how to draw that one. Okay, and then reflect it over here. At 1, 3. At 1, 3, we have a slope of -3, down 3 over 1. So that gets pretty steep, like so. And then it looks like if we take quadrant 1 and reflect it over the x-axis, we're going to get what's in quadrant 4. If you're really good at visualizing, that could be a way that you can do that. I'm just going to substitute in these coordinates. So at 1, -2, I have a slope of 2. And then I can reflect that one over there. At 1, -3, I have a slope of 3, so even steeper. And then we'll reflect that. Reflect that one over there. At 2, -1, we have a slope of 1/2, so less steep. And then at 2, -3, 2, negative 3, we have, let's see, 2, negative 3. 2, negative 3, we have a slope of 3 over 2. So up 3 over 2, it's going to be about like that. Number 16, dy dx equals x times y. So at 0, 0, we get 0. And when x is 0, actually when x is 0, the slope is going to be 0 no matter what. So when x is 0, the slope is 0. So all these have slopes of 0. And when y is 0, the slope is 0. So we have 0 slopes here as well. At 1, 1, the slope is 1. At 1, 2, the slope is 2. We're just multiplying the x and the y coordinate. So at 1, 3, the slope is 3. And at 2, 1, the slope is 2. At 2, 2, the slope is 4. It gets pretty difficult to start distinguishing these steep slopes. At 2, 3, it's 6. Okay, so that should be the steepest one. Just do your best. Negative 1, 1, the slope is negative 1. Negative 1, 2, slope is negative 2. Negative 1, 3, slope is negative 3. Negative 2, 1, the slope is negative 2. Missed my mark there. Negative 2, 2, the slope is negative 4. And then negative 6 up here. Okay. At 1, negative 1, the slope is negative 1. At 2, negative 1, negative 2. 1, negative 2, negative 2. 2, negative 2, negative 4. 1, negative 3, negative 3, negative 6. Okay. Negative 1, slope is 1. Negative 1, negative 2, the slope is 2, and then 3. Negative 3, negative 1, the slope is 3. And then we've got negative 2, negative 2, the slope is 4. And then negative 2, negative 3, the slope is 6. Number 17. dy dx equals x plus 1. So we don't have a y in our slope equation, which means that the slope is purely determined by the x coordinate. So let's first start with an x coordinate of 0. When x is 0, the slope is 1. So everywhere x is 0, we can draw a slope of 1. When x is 1, the slope is 2. So everywhere the x coordinate is 1, we're going to draw a slope of 2. When x is 2, the slope is 3. So it's getting steeper as we go to the right. Okay, at negative 1, the slope is 0. And at negative 2, the slope is negative 1. That was the easiest one yet. Number 18, dy over dx equals 1 over x plus 1. Again, we have a slope equation that doesn't have a y in it, so this means our columns are going to match. Let's start with an x value of 0. When x is 0, the slope is 1. So everywhere x is 0, our slope is 1. When x is 1, our slope is 1/2. So imagine going up 1 over 2. When x is 2, our slope is 1/3, so even less steep. At negative 1, we get 1 over 0, which is undefined. We have vertical slopes, or slopes of vertical lines, I should say. Vertical tangents. At negative 2, we get a slope of negative 1. And there we go. Number 19, consider the differential equation dy dx equals x squared times y minus 1. Sketch a slope field for dy dx at the 12 points indicated. So let's start at 0, 0. And we're just going to sub in 0, 0 into our slope equation. So we get 0 times negative 1, which is 0. So let's draw my slope of 0 there. At 1, 0, when x is 1 and y is 0, we get a slope of negative 1. At negative 1, 0, we get a slope of 1 times negative 1, so also. At 0, 1, actually anytime x is 0, we're just going to get a slope of 0. So I'll go ahead and fill those in. When x is 1 and y is 1, well, anytime y is 1, we're going to get a slope of 0. So we can fill those two in. At 1, 2, when x is 1 and y is 2, we get 1 times 2 minus 1, or just 1. So here the slope is 1. And at negative 1, 2, we also get a slope of 1. At 1, 3, we get 1 times 2 is 2. We have a slope of 2. And at negative 1, 3, we also have a slope of 2. So we've sketched our slope field for those 12 points. Part B says, while the slope field in Part A is drawn only at 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. If we look at our slope equation, we've got dy dx equals x squared times y minus 1. So I'm going to rewrite that over here. Dy dx equals x squared times y minus 1. So we're trying to figure out, when are these slopes going to be positive? Well, no matter what we choose for x, unless it's 0, because we're squaring the x coordinate, that factor is always going to be positive. So that's not going to affect the sign unless x is 0. So assuming x is not 0, this slope is going to be positive whenever y minus 1 is positive, and that happens whenever y is greater than 1. If y is equal to 1, then our slope is 0. So whenever y is greater than 1, the second factor is positive, and whenever x is not 0, this factor is positive. So x not 0 and y greater than 1. Now we can get a positive slope when we multiply a negative by a negative, but x squared will never be negative, so that's not going to happen in this case. So describe all points in the xy plane for which the slopes are positive. That's going to be whenever x is not 0 and y is greater than 1. Part C, find the particular solution y equals f of x to the given differential equation with initial condition f of 0 equals 3. We want to solve our differential equation, so we're going to start by separating variables. I want to get all the x stuff and the dx on the right, all the y stuff and the dy on the left. So I multiply both sides by dx, I divide both sides by y minus 1. And that gives me 1 over y minus 1 dy equals x squared dx. Now we integrate both sides. The integral of 1 over y minus 1. We need to do a u substitution here, but this is a really simple u sub. If you imagine u equals y minus 1, then du is just equal to dy. So this becomes 1 over u du, which integrates to ln absolute value of u, which is our y minus 1. Plus c, but we'll save the plus c for the other side. On the right, we integrate x squared dx, and we get x cubed over 3 plus our constant term c. We can solve for c now, or we can solve for y first and then solve for c. Because I have a natural log in my equation, I'm going to wait and solve for c later so that I don't have to carry some weird c value through all of my algebra. So I'm going to exponentiate both sides. E to the left-hand side equals e to the right-hand side. And let me just move that equal sign down. It looks funny way up there. And we have e to the ln something. So the e and the ln cancels out. We get absolute value y minus 1. Equals. On the right, we have e to the x cubed over 3 times e to the power c. You add exponents when you're multiplying numbers with the same base. So times e to the c. Now e to the c is just a constant, and I can call my constant term by any name I would like other than one of my variables. So I choose to keep calling my constant term c. So I'm just going to call this c. So now I have absolute value y minus 1 equals c times e to the x cubed over 3. But so I don't get confused with c's, because now I have two different values that are both called c, and I don't want that. I'm going to rename the old one, just call it c1. Now I'm going to drop my absolute value, and I do that by using parentheses and putting plus or minus in front. So c e to the x cubed over 3, and then I'm going to multiply both sides by plus or minus 1, or we could say divide both sides by plus or minus 1, and essentially that's just going to move the plus or minus over to the other side of the equation. And plus or minus c is still just a constant term, so I want to call my constant term c. If you don't like that, you can call it something else. You can keep changing the letters each time, or just leave it in that raw form. That's fine also. But since now I'm calling my new constant c, I want to call my old constant something else. So I'm just going to call it c sub 2. Now I add 1 to both sides. So I get y equals 1 plus ce to the x cubed over 3. This is my general solution. We're asked to find the particular solution using this initial condition f of 0 equals 3. So I'm going to substitute 0 in for x, 3 in for y, and then solve for c. 0 goes in for x, 3 goes in for y. So I get 3 equals 1 plus c e to the 0. E to the 0 is 1, so that drops out, and I get c equals 2. So my particular solution, y equals 1 plus 2e to the x cubed over 3. And number 20, our differential equation is dy dx equals x to the power 4 times y minus 2. Sketch a slope field for dy dx at the 12 points indicated. Let's start at the origin. At 0, 0, well, whenever x is 0, the whole slope is just going to equal 0. So at x equals 0 and y equals 0, slope is 0. At 0, 1, the slope is 0. At 0, 2, the slope is 0. At 0, 3, the slope is 0. Then at y equals 2, I can see by looking at the equation when y is 2, the slope is also going to be 0. So we get zeros there. And then let's just substitute in the other coordinates that we have left. So at 1, 0, the slope is negative 2. At 1, 1, the slope is negative 1. At 1, 3, the slope is 1. At negative 1, 0, negative 1 to the power 4, that's just going to be positive 1, and then 0 minus 2 is negative 2. The slope is negative 2. At negative 1, 1, so negative 1 to the 4th is just 1, and then 1 minus 2 is negative 1. My slope is negative 1. At negative 1, 3, negative 1, 3, I get a slope of 1. Part B, describe all points in the xy plane for which the slopes are negative. So let's look at our slope equation. Dy dx equals x to the power 4 times y minus 2. Well, x is never going to make this slope negative. X to the power 4 can only be positive or 0. So if x is 0, the slope is not negative. So we don't want x to be 0 because we're trying to figure out when the slope is going to be negative. So x can't be 0, or automatically the slope is going to be 0, not negative. And then if x is not 0, the x factor is going to be positive. So the only way for this slope to be negative would be for y minus 2 to be negative. And for y minus 2 to be negative, y would have to be less than 2. Okay, so x not 0 and y less than 2. Part C, find the particular solution to y equals f of x to our given differential equation if the initial condition is f of 0 equals 0. So let's separate our variables. We'll multiply both sides by dx, divide both sides by y minus 2. So 1 over y minus 2 dy equals x to the 4th dx. So we get ln absolute value y minus 2 equals x to the 5th over 5 plus c. This looks very similar to the last example we did. We're going to exponentiate both sides, so that's going to cancel there, and I get absolute value y minus 2 equals ce to the x to the power 5 over 5. I can drop my absolute value. It gets absorbed into the constant term c. So this was a c1, this is a c2, and this is just c, e, x to the 5th over 5. And then we add 2. So 2 plus c e to the power x to the 5th over 5. That's my general solution. And then we have initial condition 0, 0. So when x is 0, y is 0. ce to the 0, and that means c equals negative 2. So my particular solution, y equals 2 minus 2e to the power x to the 5th over 5 for my particular solution.